Hello everyone, this will be the last lecture about circular motion. This will be the last application I'll be talking about, which is the satellites and circular orbits. We talked about horizontal circular motion, we talked about vertical circular motion. Now we're going to talk about how the circular motion is applied to satellites in circular orbit around the Earth. As you all know, we have many satellites around the Earth. Some are like GPS, giving us data to find our position on Earth. Some are doing for scientific research, doing some data collected in there. So we have satellites around Earth, in short. And they are rotating around Earth in uniform circular motion. They have a velocity, also angular velocity around the Earth. And we can calculate the centripetal force applied on the object using the distance in between the object and the Earth. We also learned before when we were learning about the force of nature that there's always a force, gravitational force, applied in between any mass in the universe. If the masses are small, it's not really felt, but if we have a huge mass like Earth, it will be felt, and it is felt. I'm going to call the mass of the Earth M in here, and the mass of the satellite as M, or MS, M satellite. For a safe orbit, let's say, in equilibrium orbit, the centripetal force applied to the satellite from the rotation around the Earth should be equal to the gravitational force applied on the object by Earth. We learned that centripetal force is equal to m times AC, centripetal acceleration, which is also mv squared over r, because AC is equal to v squared over r. It is also equal to m omega squared times r. We can also use this. Sometimes it's easier to solve some questions because we know v is equal to omega times r. These are all we talked about in the beginning, the first lecture about circular motions. If you're not sure what I'm talking about here, go back and watch that lecture. And we also learned in the forces of nature lecture that F gravity, gravitational force in between two masses. Let me draw here two masses and remind you that M1 and M2. Any two masses will be pulling on each other with the gravitational force Fg, with the same force. If the distance in between them is r, Fg, gravitational force, is equal to G, universal gravitational constant, times M1 times M2 divided by r squared. Now entering these values in here for the satellite, then centripetal force for the satellite, m satellite times v squared over r, distance in between the Earth and the satellite, so we call this r, is equal to gravitational force by Earth, universal gravitational constant, times m satellite times m Earth, divided by r squared. These two forces should be equal to each other. From here, we can calculate the velocity of the satellite for safe orbit. We'll get ms cancels from both sides. One of the r here cancels with this r, and we are left with v squared is equal to g m Earth over r. V is equal to taking square root of each side. These cancels as well. G times m Earth over r. So for a safe orbit, this is the velocity a satellite should have. If we are given some values, we can apply the values, put them here, and find what the velocity should be. And g is a constant. Now let's look at some situations involving different examples. Example 1 is involving Newton's applications and this situation here. We have an astronaut in an elevator on Earth. elevator on Earth. And the elevator falling down to free fall. So A is equal to G. We solved these questions in class. And the astronaut is measuring his weight on a scale, standing on a scale. And the scale will be reading, what would the scale read? Let's say here. I know we solved these questions, we know that it should be 0, but I'll resolve it for you to remind you. What is omega 1? The weight of the person measured on the scale. And then we have a satellite in orbit around the Earth. What kind of satellite did we draw here? Okay. Doing circular motion. Let me make it bigger because there is also astronaut in here inside the satellite measuring its weight. What would the scale read in here? Let's call this omega 2 and think about it. Now, from general life, we know that here the object feels weightless. We drop this water, and anything in free fall don't feel any weight. So omega 1 will be 0. And here also we know in space, astronauts does not feel any weight, so omega 2 is also 0. Then the conclusion we come is that the satellite also should be in free fall, and it is actually in free fall. It is trying to fall on Earth, but is never hitting Earth because it is too far away. Instead of hitting Earth, it's making the circular motion around the Earth. If I ask you to compare omega 1 with omega 2, the answer would be, for W1 with W2, the answer would be they are equal to each other and 0. And here, if you want to remember again, we were saying mg is downward. What the scale read will be the normal force upward, acceleration is downwards, the total force is downward. We'll take this direction as positive and write down that F total is equal to m times a, and F total is also equal to mg plus force minus n. N is minus in the opposite direction, and mg is plus in the direction of choice, or positive. And this is equal to ma, gives us, solving for n in here, n is equal to mg minus ma. Now, if a is equal to g, we end up with mg minus mg, so 0 can be calculated. And the same thing is happening here. So if you're asked to compare the weights of a free-falling elevator with the weight of an astronaut in space, they are the same. So this is our example 1 for this lecture. Now, sometimes we can give the astronauts an artificial gravity by rotating the satellite in space. And if this rotation has the same velocity as the gravitational acceleration, centripetal force will be equal to gravitational force, and the astronaut can feel exactly like he or she is walking on Earth. Let's say we have a circular spaceship. This is spaceship. And on this circle, astronauts can walk. Let's try to make this two-dimensional, maybe, hopefully. And astronauts are walking on the surface. And Miss Earth, she wants to feel the gravity she felt on Earth, her mass, mg. Normally there is no gravity on space, so what can give this feeling of gravity could only be centripetal force. If we rotate this spaceship at an angular velocity that is large enough, or linear velocity that is large enough to give the centripetal acceleration to be equal to g. So if we say if centripetal acceleration is equal to g, then Fc is m times AC will be equal to mg, and the astronaut will feel the same gravity as she or he does on Earth. And the question here asks, in the figure we see an astronaut walking on a circular chamber of spaceship. If we assume the radius of this chamber is 100 meters, what should the angular velocity of the spaceship be? What should the angular velocity omega be in order to provide an acceleration which is the same as the gravitational acceleration? In order for AC to be equal to G, what should the omega be? You could ask me, you could ask any other value, but that's the thing. So for this to happen, if AC, we say, is equal to G, then centripetal force in the space that is applied on the astronaut will be equal to gravitational force on Earth, which is equal to mg. We also discussed that gravitational force is equal to mg, so I'm removing this now. Fc, centripetal force, should be equal to mg if AC is equal to G, because it's, as I've shown here, if centripetal force is equal to m times AC, if AC is equal to G, then it's equal to mg. So when I can write down this in terms of omega r, I can solve for the omega. Let me put it here again. We said Fc is equal to mv squared over r, or m omega squared r. This is all equal to also m times AC, all coming from the same thing. When we enter the value of AC, this is what we got. So I'm writing in terms of omega because I'm looking for omega. M omega squared times r is equal to mg will give me what should omega be. M's cancel in here. I'm left with omega squared r is equal to g. Divide each side by r. Divide by r, divide by r. I'm going slower here because some of you are having problem with these. Omega squared is equal to g over r. These cancel again. Taking square root of each side, I find omega is equal to square root of g over r. G is 9.8 meters per second squared and r is 100 meters. We should find omega from here, 0.3 radian per second. Always the unit for omega, unit for angular velocity will be 0.3 radian per second. This question is not asking for it, but go ahead and find V. If you know omega, you can get to V using omega r. And see what it is. Let me now delete this. And we have another question involving satellites and circular orbits. Okay, let's see. This one is asking about speed. We have a similar circular chamber in space. An astronaut is standing in here, called point P. At what speed must the interior surface of the space station what speed should the space station move in order so that, let me change that so very English, move so that the astronaut located in position P, or point P, will feel the same weight as he felt on Earth. I'm running out of battery here. I hope I'll make it. So he felt mg on Earth. Let me see what else is given. R is equal to, let me make this small r so you'll be able to follow same notation. 700 meters. What should we be? So the astronaut will feel the same push he felt on Earth. The push he felt on Earth is of course mg. Now he's feeling Fc. So Fc should be equal to mg, will give me this answer. I'm going to cut this short because I have to go. So Fc is equal to mg, right? And Fc is also equal to mv squared over r, will give me the answer. So from here we multiply with r, v squared is equal to g times r, v is equal to square root of g times r. 9.8 meters per second squared times 1700 meters should give us the answer for v, and it should be 129.1 meters per second. Go ahead and find omega in here as well. And what should A be? Of course G, for this to happen. Thank you and see you on Monday. I'll put a pre-lecture quiz for this one as well.